All right, so we're back in week 8, and we just did a little review on week 2, and I finished grading up to week 3. Sorry if I'm a little behind on the grading, but I'll knock that out. Well, Friday or sometime over the weekend. So let's just get back into the shell. Head down to week 8. Pumped hydro. Okay. This is a good one. The only better one is next week when you get into compressed air. And this is very relevant because the same exact system is going to be going down over at Gordon Butte. So the largest energy storage systems currently in use in the electric system are pumped hydro. There's excess or inexpensive, like at night when the wind blows, water can be pumped uphill to a reservoir. During times of higher market prices, water is drained from the upper to a turbine that makes a generator and produces electricity to sell to the marketplace. This is called arbitrage, where energy is produced less expensively during off-peak hours to store energy and released to generate energy and sold on on-peak periods. Sometimes the turbine and pump are the same device. That's the one that's going into Gordon Butte, where the motor acts as a motor and moving water uphill and is generated when it's going downhill. Same idea with the pump turbine. Okay. I'll let you guys kind of read that. I'm just going to skip ahead. Very powerful formula defines a relationship between power flow and pressure. So water horsepower I'm not going to bother that much with the derivation of this. I normally do, but in the interest of time, think of it this way. So the more gallons, and this is again getting back to our cross and through variables, I've beaten that one to death, but the more fluid that's flowing through times the pressure, so this is the through variable, this is the across variable, and then this is the basically the density and another factor that make the units work out. Because this guy's in gallons, that one's in feet, this is specific gravity. Yeah, it's all over the place. So 3960 takes care of the units. Okay, 2.31 feet is 1 psi. Sounds about right. A pound of water that's 2.3 feet tall, 1 psi, 1 pound per square inch. Okay.
Oh, that's what I was missing.
Specific gravity is 1 for water. Very easy. The brake horsepower, that's what you need to drive the pump. So it's sort of the losses, whatever things sort of eating up in friction. Yeah. There we go. 3960 converts to horsepower. Okay, input shaft power is the water horsepower divided by the efficiency. The input electrical power is the pump efficiency, you have to divide by the pump efficiency, divide by the motor efficiency. Altogether now, power to the motor is gallons per minute times the feet times the specific gravity divided by 3960 divided by the pump efficiency divided by the motor efficiency. And then if we put in the transfer, you can have yet another efficiency metric in there. Okay. Let's look at this little example. Okay. Pumped hydro storage, the fluid delivered to the turbine is 900 feet, 1200 GPM. The turbine is 98% and the generator is 95. Yeah, so let's draw a picture for this little example A. Okay. So you've got the turbine, and then you've got the generator, and you've got water coming in at so the head or the pressure. I'm just going to write it as pressure. No, I'm going to write it as head. So we use P for power. So I'll just write the head equals 900 feet. The GPM, gallons per minute, GPM equals 1200. Okay, so 900 times 1200 times 1. So fluid, I'll just write this as fluid power equals 900 times 1200 times 1 divided by 3960. And I'm going to trust the math on this and say that equals 272.7. Actually, let's just run it. 900 times 1200, whoops, divided by 3960 equals 272.7. Perfect. Okay, where is that power? That power is right here before it hits the turbine. Then the turbine output, we just multiply that by the 89% efficiency, and we get 242. Then we multiply that by the 95% efficiency, and we get 230. And then the generator, horsepower, and then we just convert the horsepower to kilowatts with the 0.746. There's 746 watts per horsepower. It's pretty impressive. Or 0.746 kilowatts per horsepower. Yeah, there we go. Oh, and what he's saying here too, rather than try to jam all the water up hill really quickly, it's going to result in a lot of turbulence losses. It's better to pump it up slowly because the friction head is like so. So if it's a water velocity squared. Well, he just says that the friction head, like the pressure that you lose, is proportional to the square of how fast it's pumping. So if you try to pump it twice as fast, you're going to lose 4 times the energy. There's always friction in the pipes.
Sure.
Yeah. Okay. The fluid power can be quantified with pressure and flow measurements. Fluid power is typically water horsepower, whether it's water or not. What are the water energy losses at each stage? What's the total system efficiency? What are the annual energy costs of the pumping system and the annual energy costs for each component? Excuse me. Problem 1. So the pump, now this is going uphill. We're actually going to run this thing uphill at 60 psi. So there's our head, and the flow is 3,000. So we'll just multiply those two numbers together, multiply by 1, divide by 3960, and that's basically the what's coming out of the thing. Right, and then you've got, okay, so let's draw this guy out. Okay, so now we're going uphill. So the water, it's coming from a lower reservoir and going to an upper reservoir. And so what you have is a motor driving a belt that drives a pump. And what we're looking at is the head equals 60 feet, and the GPM equals 3,000. So the water is going from here, up here, well, through the system, through the pump, right? And so the belt, 96% efficient, the motor, 92, so here's 92, here's 96, and the pump is 70. So the water horsepower just equals your 60 times your 3,000 times your 1. What was that other number? 3960?
Yep.
Divided by 3960. So we'll get that. And then the power is going to equal the WHP times eta motor, divided by, right? Yeah. Because the number's got to get bigger, because you're going to put more energy out than more energy in than you get out. So divided by eta motor, divided by eta belt, divided by eta P. So that's just pretty much straight up algebra. So the water horsepower, multiply those three numbers, divide by that fourth one, plug it in here, divide by your three efficiencies, bam, 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 is going to give you your power. Okay.
It's going to be power in watts.
So this is going to be, well, to get the loss, loss equals power minus, minus water horsepower. So you can basically think of the flow of the water uphill as more or less your output. So that's what you want to achieve. And then the electricity going into the motor is your input. So you're in the, and where's this coming from? Well, it's coming from the wind farm, right? So the wind farm is making electricity that drives the motor drives the belt drives the pump sends the water uphill. And so you've got this electricity coming in, and I'm just calling that, P equals electricity in, out equals your water horsepower. So again, this is there's your water horsepower, and I'll just put out. And this is your power in. Yeah. And then your losses would just be that minus that. Yeah, okay. Okay, so the motor power factor is, okay, so here's how we have to get into motor. Motor power factor is 85%. The system operates at 6,000 hours per year. Demand cost is $6 per kilowatt month. So for every kilowatt you use, let's do this one first. So $6 per kilowatt month. Let's look at that. $6 per kilowatt month. So let's say in January, you're going to run this thing at let's put a number here that actually makes sense. So first of all, 60. Oops. So 60 times 3,000 divided by 3960.
45.5.
Yeah, 45 kilowatts. Water HP equals 45 kilowatts. Now the P, let's go ahead and figure that out.
73.5.
Divided by 70, divided by 96, divided by 92. So divided by 0.7, divided by, was it 0.96?
Yep.
0.96 divided by 0.92 equals 73.5 kilowatts? Okay. 73.5. 73.5 kilowatts. So what's going on then? The power company's like, man, you're pulling a lot of juice. You're sucking energy out of the grid. And doesn't necessarily care where you're getting it from, but it's basically saying, you know what, to pump 73 kilowatts, I had to lay a lot of copper down, and I need that money back. So here it's coming back because I put in some really beefy copper 20 years ago, and I need that money back. So for January, it's going to cost you times 6 equals. It's going to cost you $441 to be running that much juice. $441 for January. So that's the so-called demand cost.
Gotcha.
You're also going to want to calculate the energy cost. You can do that already because you've got kilowatt hours. Now the other one is peak reactive cost is 28 cents per kVAR. So we need to figure out what kVAR is. Have you seen that before?
Yeah, where is it in that question?
Right here. Oh, it's here. It's sort of hidden here.
Oh. Number power factor. Okay.
So let's run that. So here's kVAR. So in any system, and I'm not sure if you've covered this in 213 or not, but this is true power down here. This is kVAR. Let's see, we need to kVAR. Let's get this kVA. Yeah, this is reactive power. No, sorry. This is reactive power here, and I don't know what that is. This is VA. So this is measured in watts. This is measured in volt amps, and this is reactive power. So this is sometimes called kilowatts down here. This is called kilovolt amps, and this is called kilovolt amps reactive. And yeah, it's the way. Yeah, so the way this works is power factor equals true power over VA so in this case we know what the let's see, what do we know? I'm trying to decide if we actually know the true power or if we know the volt amps from the problem. It's 6,000. What's the power? Think about that for a second. Because we've already calculated that the thing is running at 73.5 kilowatts. Yeah, so VA is going to be larger than that. Yeah. So what we have is VA equals true power over power factor. So in this case, the VA equals the true power, which we came out to be 73.5, divided by 0.85, divided by 0.85 equals 518, or 519. No, it's not right. What did I do wrong? 73.5 divided by 0.85. 73.5 divided by 0.85. 86. KVA. Now kVAR equals the square root of true power squared plus kVA squared. Times 86.5. $74.80. Then true power, what was that? 73.5 squared? 73.5 times 73.5 equals 5402. 5402. Run out of space, that's okay. 5402 plus 7480 plus 7480, 12,882 equals, there's a square root around this thing. It seems too high to me. Oh, I did it wrong. Shoot. Sorry. Forgot the Pythagorean Theorem. It's not that. Sorry, kVAR. We've got the numbers. We can do it really quickly. kVAR, I just put the wrong number in for the hypotenuse, equals the square root of kVA squared minus true power squared. There we go. It's going to be smaller. So it's the square root of 7480 minus 5402. Let's do that instead. All kinds of ways to make mistakes around here.
About 46.
$74.80. Equals, yeah, 46, perfect. Equals 46 kVAR. Okay, now back to the problem. 28 cents per kVAR month. So if we're running at 46 kVAR times 28 cents, and really it's going to charge you 28 cents every time. It's not going to keep charging you like every single day, but it's, if you hit whatever maximum k-var you hit is what it's going to charge you. So that 28 cents is kind of factored into it. It might be like 1 cent per k-var per day, but if you're running for 30 days, you know, or 28 days, it's basically, that's the whole month's charge. It's a little bit weird. But so let's multiply that by 28 cents per k-var month, I think. Okay. Doesn't seem like enough, but 45. We're at 45 k-var. So times 28 times 0.28 equals 12 bucks. That doesn't seem like quite enough. I'm gonna have to email my man on that. You're like, why even bother? 12 bucks a month.
Right.
Bucks per k-var month. There may be something else up here in the reading. Let's take a look. Measuring current. Doesn't seem like enough. Or I'm gonna call it right here.